Okay, so the previous session was a little bit about center of mass, the concept and the computation, right? We'll now look at interaction of particles with mass, how they mutually interact, and what are the ways in which they could interact with each other, right? This would be the objective of the session today. So, in a minimalistic manner, if I could suggest a few things. First of all, if this is a surface, say S1, right? And this is another surface, call it S2. This is another surface, refer to this as S2. Now this is a tangent, a common tangent to the two surfaces. This is a common tangent to the two surfaces. This direction, sometimes called the common tangent direction, or also referred to as the parallel direction. Parallel direction. Parallel direction. This is the purview of friction. Relative motion between the two surfaces in this direction will give birth to frictional forces that they could exert on each other if they were rough, right? So this direction belongs to friction, the common tangent direction or the parallel direction. Whereas this direction, which is perpendicular to the common tangent along the area of tangency, is called the common normal direction, or sometimes just the normal direction. These two surfaces could interact with each other both along the parallel direction and along the normal or the common normal direction. Along the parallel direction, they would interact courtesy friction. Whatever they do to each other in this direction, along the common normal direction, interaction means exerting forces on each other, right? When they are capable of exerting forces on each other in this direction because of some interaction, then that interaction in the common normal direction is called collision. Interaction along this direction, exerting forces on each other in this direction, is collision. The normal direction belongs to collision, right? Now, collision essentially then would be an event conventionally assumed to be taking place for a very short time. Assumed to be taking place for a very short time. And say if this surface exerts a force on this surface F in this direction, then this surface will exert on S1 a force in this direction, constituting an action-reaction pair. Constituting an action-reaction pair. Right? Although, in a more liberal sense, they end up saying, well, collision could take place even if surfaces are not in contact, but we'll take to the more orthodox view on collision, where there is physical contact between the two surfaces. Forces that surfaces would exert on each other when they are not in contact, that means action at a distance forces, we will not look upon those forces to be following within the jurisdiction of collision. right? So we would assume that the surfaces are interacting, are in actual physical contact and exerting forces on each other in this direction. That event, if taking place for a very short time, is referred to as collision, right? Now, when they exert forces on each other in this direction, then what really transpires is that their area of contact, their region of contact, this is the region of contact. There is an area of contact of the two surfaces that has some elastic properties, Now, this event, collision, which is taking place for a short time, delta t, causes this region of contact to get deformed. This region of contact gets deformed. When it gets deformed, it becomes party to what's called strain energy, also elastic potential energy. See, like a spring, when it gets deformed, it becomes party to elastic potential energy, half kx square. In exactly the same way, you know, there is a spring kind of a behavior of the two surfaces when they interact with each other. There is a spring kind of a behavior that they have. They respond to application of forces. They get deformed under the influence of forces because of their elastic properties, and therefore when subject to deformation, they store what's called deformation energy or strain energy or elastic potential energy. Get deformed, and therefore there is what's referred to as strain energy or deformation energy. Or elastic potential energy. When matter gets deformed and it's capable of getting restored to its original shape and size, then you know the energy that it stores during deformation is referred to as elastic potential energy or strain energy or deformation energy. We have looked at one instance of strain energy, the energy in a spring, right? So, however, the forces that they exert on each other, you know, these are internal forces. So, during the when they interact with each other, then there is an instant before they started interacting, that is just before interaction. There is a regime just after interaction, and there is a regime during interaction. That regime is collision during interaction, and that lasts for a very short time theoretically, right? These forces F that they exert on each other, that are colliding forces, forces of collision or impact forces, the ones that they exert on each other in the common normal direction, they are generally of very large magnitudes, and acting for a very short time. That's impulse only. It's not like impulse, it's impulse. Each of the surfaces will exert on the other surface an impulse equal in magnitude but oppositely directed. Now, S1, because of the impulse that it exerts on S2, will change the linear momentum of S2. S2, because of the impulse that it exerts on S1, will change the linear momentum of S1. However, since they exert equal and opposite impulses on each other, they would change the other's linear momentum by the same amount but in opposite directions. Therefore, the net change in linear momentum because of this internal impulse is 0. The system preserves its linear momentum despite collision. It preserves its linear momentum in absence of an external force, right? However, the constituent elements S1 and S2, their individual linear momenta is likely to change. The linear momentum of S1 and S2 will change, but the total linear momentum that they had before they started on an interaction spree remains the same at all times. Right? So, the cardinality of this interaction is that it does not result in change of linear momentum. That's cardinal to this interaction. That's cardinal to this interaction. However, the strain energy, that is the strain energy that develops because of deformation, localized deformation of the interacting bodies, that might show and exhibit different kinds of behaviors during the period of interaction, for sure. During interaction, that means during that short time delta t, when they are interacting with each other, the colliding units start to get deformed in the localized area, start to get deformed locally. Now, that energy of deformation, that is the strain energy, that becomes prominent during that time delta t, comes at the expense of the kinetic energies of the interacting particles. The strain energy or the deformation energy that develops during delta t, the strain energy that develops, it has to come from somewhere. It comes at the expense of kinetic energy. That means during this interaction, the kinetic energy gets consumed to give way to strain energy, Kinetic energy reduces during interaction. The colliding units start to get deformed, store more and more of deformation energy. The kinetic energy, total kinetic energy of the colliding units decreases. So now, based on the elastic properties of the colliding units, there is a behavior that we want to classify for colliding units interacting in the common normal direction, right? But even before I model that behavior, just a couple of remarks. Let's say if this is one spherical surface, and say it has the center of this has a velocity v1 like this, right? Another spherical surface, center c2, and it has a velocity v2 parallel to v1, right? Perpendicular to the line joining the two centers. Now, in this case, this line joining the two centers, is really the common normal, is the normal direction. This is the direction. If anything happens in this direction, that's referred to as collision. This is the normal direction, C1, C2, right? This perpendicular to C1, C2 belongs to friction, This is the common tangent direction and it belongs to friction. Now, are these two particles colliding with each other? No, because there is nothing that is happening in the common normal direction. They are not colliding. This is not collision. These particles are only brushing past each other. That's all. They are not colliding. When they brush past each other, do their velocities change? Depends. If they are rough, then realize that there is relative motion in the parallel direction of the two surfaces. Therefore they will exert frictional forces on each other, and therefore their velocities will change. If they are rough, they would know that they have brushed past each other. If they are rough. However, if they are smooth, will the velocities of the two change? No, because it does not invoke friction, because there isn't any, right? And the two particles don't even know that they have brushed past each other. If they are smooth, they won't even know that they have actually brushed past each other. That's the story. That's the story, right? So that's not collision. However, if the particles, say if this one had a velocity v1 like this, and this had a velocity v2 like this, then they are interacting along the common normal direction, the line joining the two centers, and this situation is referred to as collision. This situation is referred to as collision. Interaction along the line joining their centers or the common normal direction falls within the jurisdiction of collisions. So this is collision, this is not collision, right? If one particle had a velocity v1 like this and the other particle had a velocity v2 like this, is this collision? Yes, because there is a component of v1 along c1 c2 which results in interaction along c1 c2, and therefore this is collision. This is collision.
If v2 is greater than v1,
They will not interact, obviously. I mean, I'm saying these are algebraic v1 and v2. अरे बाबा कांटेक्ट में ही नहीं आएगा तो किस चीज का कोलिशन, भाग जाएगा, राइट? No, I'll not screw up your Diwali, don't worry. I will not screw up your Diwali. You carry so much of responsibility on your head. So in any case, you understand then, right? This kind of a collision where the velocities of both the colliding units are along the line joining their centers, that means in the common normal direction, this is a head-on collision. This is a head-on collision. Where the velocities of both the colliding units are along the line joining their centers, that means along the common normal direction, that collision is called a head-on collision or a headlong collision, right? If the velocity of at least one particle is not along the line joining their centers, then this collision is called an oblique collision. If the velocity of at least one particle is inclined to the line joining the two centers, is inclined to the line joining, where theta is not 90 degrees. Theta is not 90, because if theta was 90 degrees, there would be no interaction along the line joining the two centers. Theta is not 0. Theta is a number lying between 0 to 90 or 0 to 180 also, as long as theta is not 90 degrees, right? Then this collision is called an oblique collision. This is an oblique collision. If not both the velocities are along the line joining the two centers, then the collision is an oblique collision. This is an oblique collision. Huh? That also. See, if a collision occurs like this, say this is V1, this is V2, say this angle is theta 1 and this angle is theta 2, then this collision is also oblique. I am saying even if one of the velocities is inclined at an angle theta with C1, C2, then the collision is oblique. If both are inclined at an angle theta, then that collision is oblique anyways. This is the most generalized oblique collision, right? Clear? Now, so an oblique collision actually has two constituents, because you could, for the two colliding units, let's say this has an x component of velocity, this has a y component of velocity, component of v1 in this direction, component of v1 in that direction. Similarly, this could have had, say, v prime x, and this is v prime y, right? Generalized collision. Now Vx and Vx prime are participating in collision, whereas Vy and Vy prime belong to friction, right? Now all that collision will do, collision is incapable of changing the linear momentum of the system. It will change the linear momentum of the individual particles, but not the total linear momentum of the system. So if at all, collision will redistribute linear momentum. It has the same total linear momentum before and after. It might only redistribute the linear momentum. I mean, in the sense, the total linear momentum just before impact of the two particles is, say, 10 units. The first one has 4 units, the second one has 6 units. After collision, the first one might have 6, the second one might have 4 units. That means there is redistribution of linear momentum. It houses the same total linear momentum in any given direction. That's not going to change, right? Now, suppose we're talking of two colliding units in a state of head-on collision. Say this one had a velocity v1 along the line joining the two centers, and this one had a velocity v2 along the line joining the two centers. This is a state just before collision. JBC, we'll call it just before collision. They just started to collide. Then there is a regime during collision. This happens for a short time, and there is localized deformation. At the expense of the kinetic energy of the colliding units, right? Their velocities keep changing, v1 prime and v2 prime. They keep changing. There is a variation of v1 prime and v2 prime during collision. We'll examine that. And then there is a state, after that state, there is a state just after collision, where, say, this one becomes v1 double prime and v2 double prime, for example, right? This is the state where this is done and they start to part, and after this no further interaction occurs, right? They don't interact from this state onwards. Okay, now I'll focus on this state, the short time of interaction that takes place between the two colliding units, where they locally get deformed, right? So essentially, when I say they get locally deformed, it really means, say, suppose this was C1, this was C2, this mass was M1 and this mass was M2. I could model it. See, when they get deformed, then the region of deformation behaves like a spring. So I can effectively equivalently assume that this arrangement in a simplistic manner could be modeled to an arrangement of this kind, M1, M2, with the region of deformation being replaced by a spring of force constant Kc. Because see, when they start to interact, this has a velocity v1 and this has a velocity v2, and this is the region that gets deformed during this interaction. This is just before interaction, where they had velocities v1 and v2. The spring actually represents the localized region which gets deformed, right? So we would look at this as the model during this short time delta t and examine what happens, right? So the deformation, localized deformation that we are talking of the colliding units is represented by the compression or elongation of the spring as is relevant. Deformation of the spring represents that localized deformation that takes place in the colliding units, right? Okay. So we have these two masses m1 and m2, and just before collision this had a velocity v1, say bigger than v2, this had a velocity v2. Let me call this end p, this end q, say v1 greater than v2. And the spring initially just before collision they were not deformed, so we have the spring in its natural state. So the spring is in its natural state initially. The spring is in its natural state initially, right? Okay. The displacement of the masses during collision, you know, physical movement is negligible, Now, now, see, if this end has a velocity higher compared to this end, what would happen to the spring? It will get compressed, right? The spring starts getting compressed. So now, whatever I am talking of is for that short time of interaction, delta t, right? So then, spring starts getting compressed. If it starts getting compressed, what will happen to the kinetic energies of the colliding units? It will decrease, because the energy of compression, the deformation energy in the spring is coming at the behest of the kinetic energies of the colliding units, right? Say this was when the spring starts getting compressed, P and Q start coming closer together, start to cave in, and the velocity of this, say, becomes v prime. This is an intermediate velocity during compression. This is velocity v2 prime, right? Now, when the spring starts to compress, starts getting compressed, when the spring starts getting compressed, it would want to unfold. It would like to unfold. Now, in its attempt to unfold, it will exert a force on m1 in this direction. It will exert a force on m2 in this direction, right? So, what is it going to do? It will retard m1, it will accelerate m2, right? It will retard m1, it will accelerate m2, right? So, m1 gets retarded, m2 gets accelerated. m1 gets retarded, m2 gets accelerated, right? So the velocity of this particle decreases, the velocity of this particle increases, right? Initially the velocity of this is higher compared to this. However, during this regime, as long as the velocity of this is larger than the velocity of this, the spring will keep getting compressed, right? Its compression levels will go on increasing, right? So the velocities of the two particles, velocity time during the short time delta t, for m1 the velocity decreases. This is for m1, the velocity decreases, right? It started with a velocity v1 and its velocity decreases because of this retarding force, right? The velocity of m2, because of this accelerating force, the velocity of m2 will increase, right? Right? Now, at some instant, their velocities will become equal. At some instant, their velocities will become v. The velocities of both will become v at some instant of time. Yes or no? Right? Isn't it? Now, when the velocities of p and q both become the same, the spring will not get compressed any further. Right? The spring will not get compressed any further. Now, however, the velocity of m2 continues to increase, the velocity of m1 continues to decrease. So then, there is a state during collision. There is a state during collision when the velocities of both the masses becomes the same, right? And however, during this regime also, is there any change in the total linear momentum of the system? No. The particles m1 and m2 brought a linear momentum m1 v1 plus m2 v2. And in some intermediate state during collision, the velocities of both the colliding units is going to become v. That means at that instant the total linear momentum of the system is v, and that does not change. This is during an intermediate state where the velocities would have become the same, right? Right? Even at an earlier instant, if let's say the velocity of p is v1 prime and velocity of q is v2 prime, then m1 v1 plus m2 v2 is m1 v1 prime plus m2 v2 prime. I'm saying the total linear momentum does not change. The system had a linear momentum m1 v1 plus m2 v2. It remains the same at all times. So if at an intermediate state both the particles acquire a common velocity v, then the total linear momentum would be m1 plus m2 into v. That's all that I'm saying. Got me? Let me just be done with this. I think all your questions will get addressed. Yes. Huh? Yes, because are there external forces? Then why should the linear momentum change even during compression or elongation or deformation of the spring? Linear momentum is not going to change. Certainly. Sit down. So for sure, you would expect at some instant, at some state of the spring, the velocity of this end is p, the velocity of this end is also v. How do you know how much of deformation energy is there in this state? The kinetic energy relinquished till this point must have appeared as deformation energy in this, right? What was the total kinetic energy that we had? Half m1 v1 square plus half m2 v2 square. Now in this intermediate state, the kinetic energy that the system has is half m1 plus m2 into v square. So this minus this will give me the loss of kinetic energy till this point. This is the loss in kinetic energy till this point, yes or no? Right? And if this is the loss in kinetic energy till this point, this must be the energy of deformation in the spring. Right? This must be the strain energy till this point. This must be the strain energy, the energy lost till this instant when their velocities become same, where v can be obtained from linear momentum considerations m1 v1 plus m2 v2 would be m1 plus m2 into v. That v is obtained from these considerations, right? Now, from this point onwards, the spring is still in a compressed state, deformed state, right? It will exert on m1 a force in this direction, on m2 a force in this direction, variable force, because that depends on the extent of compression, right? So the velocity of m2 will increase, the velocity of m1 will decrease. Yes or no? Now, from this point onwards, we will start to characterize the nature of collision. That means you understand that till this point, the spring has got compressed, deformation energy obtained out of the change of kinetic energy, linear momentum has stayed put at all times, right? The total linear momentum of the system, right? Now, realize that based on the spring, let's say there is a spring which says, now I have consumed this amount of deformation energy, I'm incapable of giving you back the deformation energy that I have used up from your kinetic energy domain, right? Then the two particles would have to reconcile to the fact that no further, and the spring says, okay, so the spring says I will not unfold any further. That could be a certain spring, that spring is inelastic in character, is an inelastic spring in character. It says, no, I've got compressed till this extent, now the velocities have become the same. True, I cannot get compressed any further, the spring cannot get compressed any further because P and Q have acquired the same velocity, but a good spring had the capability of unfolding. But a bad spring, theoretically, didn't have the capability to unfold. It says, I can stay at this level. Good, I can't get compressed anymore, but I can't unfold anymore either. I'm not as elastic as other springs. I cannot unfold any further. And the states of the two masses will remain this only at all times. That's one kind of spring. So one kind of colliding masses, right, would behave this way, where the deforming units stay deformed at the maximum level, which is this. This is the maximum level of deformation of the spring. So the maximum deformation level of the colliding units is what it represents. Maximum deformation level of the colliding units is what this represents, right? Yes or no? So one spring says, no, this is the level I will maintain. And then the two masses resign to fate. They say, all right, so we move with a velocity v at all times. Therefore, if they are moving with a velocity v at all times, that means now they are moving together as a combined unit. Together they move as a combined unit, right? They are not parting. After this, they are not parting. And if a collision of this kind takes place, where after collision the two masses move as a combined unit, where there is great amount of loss of kinetic energy which stays resident as deformation energy in the deforming bodies, then that collision is the worst kind of collision in terms of energy, and this is called a perfectly inelastic collision. This is a perfectly inelastic collision. Momentum does not change, but there is a maximum possible loss of kinetic energy, right? Loss in kinetic energy is this. Initial minus final is the loss in kinetic energy. Clear? Now, then the other variety of a spring, where the spring says, all right, I've got deformed till, so everything from this point onwards, right? This state is certainly arrived at, right? Now from this point onwards, one possibility is this, where the two masses then move with a common velocity. It's a perfectly inelastic collision. Now the other possibility, where the spring says, all right, I've got compressed by 3 centimeters. I mean, just to represent what's happening in the deformation, right? Now, I can't give back the entire 3 centimeters. I can't come back to my natural state, but of the 3 centimeters I've got compressed, I can release part of the compression. I can release part of the deformation. That means it does not release all its deformation, because as and when it starts to release deformation, that deformation energy would appear as kinetic energy of the colliding units. Therefore, there is restoration of kinetic energy of the colliding units if it starts to unfold. So it says, no, I will not completely unfold. I will not completely get back to my natural state. I will maintain some amount of deformation in me. There will be some amount of deformation that will be resident in me, but some part of the deformation I would give away, and that will appear as kinetic energy. That's the second kind of collision that takes place, right? So if that means part of the deformation gets released, not completely, gets released, and there is partial restoration of kinetic energy, and there is partial restoration of kinetic energy. There is partial restoration of kinetic energy. Then part of the deformation energy gets released. Only to that extent the original kinetic energy gets restored, but not completely, right? So there still is loss of kinetic energy in the state, but less than the loss of kinetic energy in this state. This kind of a collision where there is partial loss of kinetic energy, not a maximum possible loss of kinetic energy, this is called just an inelastic collision. And this could be quantified. There could be a collision which is more inelastic, there could be a collision which is less inelastic. More inelastic means more amount of deformation energy stays resident. Less amount of deformation energy is released, that's more inelastic. Less inelastic would be one in which there is more release of deformation energy, appearing as kinetic energy, more restoration of kinetic energy, that will be less inelastic, right? And then there is this very good spring which says, good, I've got compressed to this degree, I have no reason to hold back the deformation that I got from kinetic energy. I'm going to give it back completely to kinetic energy, and this spring completely unfolds to its natural length. It does not hold back any part of deformation. All the deformation that it had received, it gives back to the kinetic energy, and the original value of the kinetic energy gets restored, right? So that spring where there is complete release of deformation, there is complete release of deformation, complete restoration of kinetic energy, this kind of collision is really ideal, and it's called a perfectly elastic collision. It's called a perfectly elastic collision. Where the kinetic energy just before collision, during collision there is loss of kinetic energy because the spring will anyways get deformed, but then it releases back the deformation, gives it back to kinetic energy, and there is complete restoration of kinetic energy. Kinetic energy before collision and kinetic energy after collision will be maintained. No, that will change. See, like I said, in a very general sense, the velocities of the colliding units will change, but the total linear momentum of the system will remain preserved. Yes, the velocities will change.
The amount by which one velocity
See, if you realize from this point onwards, this will still accelerate and this will still retard. That means now the velocities are becoming different because they have a common velocity here. This will increase, this will decrease in a situation of this kind. So now, is there any possibility for the velocities to remain the same? No? Because do you realize that velocity of this has decreased from v1 to v, and it will further decrease. The velocity of this has increased from v2 to v, and it will further increase. So there is no prospect of the velocity remaining the same of the colliding units, right? There would be an individual change in linear momentum of the colliding units, but the total linear momentum of the system remains the same in any given direction if there are no external forces imposed on the system. Clear? In all these cases, there is one thing common though, which is conservation of linear momentum. These three broad categories of collision differ only to the extent of the loss of kinetic energy that takes place. In a perfectly inelastic collision, there is a maximum loss of kinetic energy. In an inelastic collision, there is a loss of kinetic energy, but less than what results in a perfectly inelastic collision. In a perfectly elastic collision, there is no change in kinetic energy, right? Got me? So now, that was the end-to-end dynamics of the regime delta T of collision, right? So in a head-on collision, let's say, if this particle was mass m1, velocity u1, this one mass m2, velocity u2, and they collide. This is just before collision. This is just before collision. And say, just after collision, the velocity of this becomes v1 and the velocity of this becomes v2. Just after collision, then no matter what the nature of collision is, no matter what the nature of collision is, the total linear momentum stays put. That means, say in this case, m1 u1 plus m2 u2 must be the same as m1 v1 plus m2 v2. And now these numbers u1, u2, v1, v2 are algebraic numbers. That means if I have chosen everything in one direction positive, then in the other direction it's going to be negative. Say if everything in this direction was positive and this was 3 meters per second this way, then u1 would be plus 3 meters per second. If u2 was say 4 meters per second this way, then u2 would be minus 4 meters per second. So these numbers u1, u2, v1, v2 are algebraic. So algebraic linear momentum remains the same before and after collision. As far as the kinetic energy is concerned, in a perfectly elastic collision, the kinetic energy half m1 u1 squared plus half m2 u2 squared must be the same as half m1 v1 squared plus half m2 v2 squared. Kinetic energy remains the same before and after, right? In a perfectly elastic collision. Now if I collected terms here, say for example in this case I wrote m1 into this equation, the momentum equation, the energy implication, this was m1 into u1 minus v1 equals m2 into v2 minus u2. That's equation 1, just rewritten, transposing terms, right? And this equation, the second equation, m1 u1 squared minus v1 squared is m2 v2 squared minus u2 squared. That's terms transposed into, right? Now if you divide this by this, then what you would end up getting is the following. You would get v2 minus v1 by u1 minus u2 as 1. On dividing, this is what you get. You can check that later on. Trust me on this, right? You would get v2 minus v1 by u1 minus u2 as 1 is what you'll get on dividing. Now, this number, which is, look at the numerator, it's relative velocity of separation, v2 minus v1. And look at this, this is relative velocity of approach. This number, this expression, just this expression, forget its value. This expression, v2 minus v1 by u1 minus u2, this expression is actually relative velocity of separation divided by relative velocity of approach. Along the common normal, everything along the common normal. This is relative velocity of separation along the common normal divided by relative velocity of approach along the common normal. Where, again, these numbers have to be algebraic. You know, for example, I have taken everything in this direction positive, and this v1 turned out to be 6 meters per second like this. Then in this expression, v1 would be minus 6, right? And say u2 was 3 meters per second like this, then this u2 would be minus 3. So all these terms here, all these entities here are algebraic. That means u1 u2, v1 v2 are all algebraic based on a choice of direction as positive and negative. These would be all algebraic entities. Also in this expression, if I took numerator as 2 minus 1, then the denominator should be taken 1 minus 2. If the numerator is taken 2 minus 1, if numerator is taken 2 minus 1, that means velocity of second particle minus velocity of first particle after collision, then the denominator should be taken 1 minus 2. That means these are velocities before collision, these are velocities after collision, right? These are algebraic differences, and if I took numerator 1 minus 2, then denominator should be taken 2 minus 1. That's important thing, right? This quantity actually determines the nature of collision in terms of the elastic quality of collision. In a perfectly elastic collision, this is 1. In a perfectly elastic collision, this will always be 1 in a perfectly elastic collision. Now, in a perfectly inelastic collision, V1 and V2 both will be the same. In a perfectly inelastic collision, V1 and V2 both will be the same. Did I tell you? During the collision regime, after they acquire a common velocity, the spring stays put in that state and the two particles move together in tandem with a common velocity v. They move with a common velocity v in a perfectly inelastic collision. So, in a perfectly inelastic collision such as this, this expression v2 minus v1 by u1 minus u2 becomes 0. In a perfectly elastic collision, this expression is 1. In a perfectly inelastic collision, it will be 0 because relative velocity of separation is 0. They move together, so there is no relative velocity of separation. So this is 0. That's a perfectly inelastic collision. Perfectly inelastic collision. That's a perfectly inelastic collision. Right? In a collision which is inelastic, right? That means that's a state between perfectly elastic and perfectly inelastic. That's an inelastic collision. Collision, this expression v2 minus v1 by u1 minus u2 lies between 0 and 1. So, this ratio has some importance. It will determine the nature of collision. If this lies between 0 and 1, it's an inelastic collision. If it's 0, it's a perfectly inelastic collision. If it's 1, it's a perfectly elastic collision, right? Therefore, there must be a name given to this. The name given to this expression is E. E, v2 minus v1 by u1 minus u2. It's called coefficient of restitution. It's called coefficient of restitution. So if E is 0, what kind of a collision is it? Perfectly inelastic. If E is 1, it's a perfectly elastic collision. If E lies between 0 and 1, it's an inelastic collision. The closer E comes to 0, the greater is the loss of kinetic energy. If E comes closer and closer to 1, the loss in kinetic energy is lesser and lesser, right? So, E equal to 0.3 versus E equal to 0.7, in which case there would be more loss of kinetic energy, 0.3, right? So, smaller values of E closer to 0 will result in greater loss of kinetic energy compared to values of E closer to 1, right? Now, so one thing that is guaranteed is all kinds of collision will be about preservation of linear momentum for sure. Then based on the value of E, the coefficient of restitution which determines the quality of collision, we have either a perfectly elastic collision, perfectly inelastic, or an intermediate state of collision which is an inelastic collision. E can lie anywhere from 0 to 1. Now, if there are two identical masses, say this is M and this is M. These are two identical masses, and just before collision, they have velocities u1 and u2 are their velocities just before collision. Identical masses colliding head-on collision. Velocities u1 and u2 just before collision, right? And just after collision, say their velocities are v1 and v2 after collision. Right? And say the collision is perfectly elastic. Say the collision is perfectly elastic. Say the collision is perfectly elastic. All right. So now, the linear momentum, irrespective of the nature of collision, will be the same before and after collision. That means P equal to constant would mean M1 mu1 plus mu2 must be mv1 plus mv2. That's guaranteed. That's guaranteed. Now, since the nature of collision is perfectly elastic, there are two mathematical things that we can do to suggest that the collision is perfectly elastic. Either I could say kinetic energy before collision equal to kinetic energy after collision. That means half mu1 squared plus half mu2 squared is half mv1 squared plus half mv2 squared. That's one of the two things that we could do. But then that's a quadratic expression, right? It has greater complexity, algebraic complexity. So instead of saying kinetic energy equal to constant, we use a superior substitute for kinetic energy. We instead say E is 1. Instead of saying kinetic energy equal to constant, we say E equal to 1. That's a superior substitute for kinetic energy. E equal to 1 will guarantee that the kinetic energy is the same. So would you not prefer to use E equal to 1 compared to saying half mu1 squared plus half mu2 squared, etc.? Right? You would rather want to say E is 1 for a perfectly elastic collision. That means V2 minus V1 by U1 minus U2 must be 1. Relative velocity of separation by relative velocity of approach must be 1. Right? Now, so both physicalities have been consumed, linear momentum, and this actually is out of a combination of linear momentum and kinetic energy, because we divided the two equations, right, linear momentum and kinetic energy equations, to get E equal to 1 for a perfectly elastic collision. So in any case, we have used up the physics of the problem. So now this gives us, if I had knowledge of U1 and U2, then there are two unknowns, V1 and V2, and I can solve for V1 and V2 from these equations. When you solve for V1 and V2 from these equations, you will get V2 equal to U1 and V1 equal to U2 is what you will get. When you solve these equations for V1 and V2, simultaneous equation, you will get V2 equal to U1 and V1 equal to U2 is what you will get when you solve these two equations. Right? Now, I mean, that you can check. Don't doubt me on this. That will happen. Okay. Now, what it really means is that if there are two identical particles in a state of perfectly elastic collision, then their velocities get interchanged. That is what is happening. Right? This one is taking up the velocity of this one, and this one is taking up the velocity of this one. Suppose this was 5 meters per second and this was 3 meters per second. After collision, this will be 5 meters per second and this will be 3 meters per second. So if two identical particles collide head on, then in the normal direction, in a state of perfectly elastic collision, their velocities get swapped. Yes or no? No? Convention, yaar, convention. So now, can I wipe this off? Yes. Hmm? How do we analyze this? You mean, well, if you really ask me, there is no special physics about this. I mean, because the two masses are identical, it gets cancelled. So there isn't a physics about this. In fact, for if you really think about it, you know, V2 minus V1 by U1 minus U2, that's merely mathematical now from this point onwards. So there isn't anything special in the physics involved with this. Trust me, right? This is merely mathematical. I mean, for both the things to have got accomplished, momentum and kinetic energy, this has to happen. That's all, right? So I don't read too much into that. Now, say if there are two colliding units and one of them is really heavy, right? One of them is really heavy. Say this is a heavier and this is a lighter colliding unit. This is initially at rest, say, and this is moving this way. Capital M much larger compared to small m. See, heavy and light are relative terms, right? I mean, if I collide with a 250 kg man, then that's going heavy compared to me, all right? But if this 250 kg man collides with Jupiter, then really light compared to Jupiter, right? So when I say really heavy, it's heavy compared to this. That's what it means. You know, it could just be 2 kgs and this could be just a milligram. So then this is even 2 kgs is heavy, right? So now M much larger compared to capital M much larger compared to small m, and this small m charges into capital M. Okay, charges with a velocity v naught, say. Right? Now, what's going to happen is there would be a collision, but this fellow will not feel the heat of collision. Stay at rest, almost practically. That's a good approximation to assume that will stay at rest despite the collision. This guy stays at rest after collision also. And this poor fellow gets rebounced with, say, velocity v1. That's the result of this collision, right? Now if this happens, so when one of them is really massive, capital M, then if someone gave you v naught and v1 and said compute coefficient of restitution for this collision, then realize that in order to calculate coefficient of restitution, I'll say relative velocity of separation divided by relative velocity of approach along the common normal, both along the common normal, right? So in the numerator, I'll take both the velocities after collision. In the denominator, just before collision. So if in the numerator I take capital M minus small m, then in the denominator I'll take small m minus capital M. This will represent the states of the numerator, this will represent the states of the denominator, right? So, and let's say I take everything in this direction positive, everything in this direction positive, say. Yeah, you confused? Why are we taking? Sorry? Huh? No. When I say this mass minus this means velocity of this mass minus velocity of this mass. That's what I mean. right? So that's shorthand. Okay, so relative velocity of separation, say, so I'll take 0 for this final state, minus velocity of this, I'll take minus v1, right? So minus v1, right? So it will become plus v1. So if in the numerator I have taken this minus this, then in the denominator I'll take this minus this. That means their velocities, right? So in the denominator it's going to be v0 minus 0, right? It remains 0. So that gives us v1 equal to E times v0, v1 equal to E times v0. So if E is a property given to you, the coefficient of restitution for the collision, then the velocity of rebounds is going to be E times the velocity with which it hits, is going to be E times the velocity with which it hits, right? Now, suppose there is a very heavy tray lying on a horizontal surface, heavy tray. All right. And there is a ball, small m, whose mass is small compared to the heavy tray, right? And its small mass moving with a velocity v0 like this, right? So it goes from A to B, it collides here and comes back to A. That's a round trip. A to B and back to A is a round trip. A to B and back to A. That's a round trip. Now in a round trip it was found that the average speed of mass m in a round trip is v0 by 3, Now, where on earth does the collision take place? It takes place here, and it rebounds, and it completes a round trip, right? So, now, what is E for the collision occurring at B? We want to find the coefficient of restitution for the collision occurring at B, right? Now, from A to B, it continues to move with velocity v0. Nothing that will change its velocity, right? At B, it undergoes a collision, and when it undergoes a collision at B, it rebounces with a velocity vr, which is E times v0, because this is very massive. The velocity of rebounds therefore would be E times the velocity of impact along the common normal. That will be the velocity of rebound, right? Now, what's the average velocity in a round trip? Average velocity is 0 in a round trip, because total displacement by total time. So in a round trip, total displacement is 0, right? But if I say average speed, then that's going to be total distance traveled by total time taken. That's the average speed, right? Total distance traveled by total time taken, that's going to be the average speed. So if I have to calculate the average speed independently, then suppose the length of the tray is L0, right? So average speed, now in a round trip, what's the total distance traveled? 2L0. 2L0 is the total distance traveled in a round trip, divided by total time taken to go from A to B and then from B to A. Now what's the time taken to go from A to B? L0 by V0. L0 by V0 is the time taken to go from A to B, and then from B to A, L0 by EV0 it returns with a velocity ev naught. So the time taken to return is going to be L naught by ev naught. That's the average speed in a round trip, and that's given to be v naught by 3. That's given to be v naught by 3. Yes or no? So you can solve for E from these considerations. L naught will get cancelled, this v naught will get cancelled, and you can solve for E. Right? Isn't it? Okay. Now, clear now? What does E turn out to be? 6 minus 1, 5. 1 by 5. E is 1 by 5. Coefficient of restitution is 1 by 5 for this collision. Right? Can I wipe this off? Now suppose this is the surface of Earth, horizontal surface, and say there is a small particle mass m. We will assume that this is not Jupiter, okay, and it falls from a height h, right? Starting from rest, Diptesh, it falls from a height h. So when it hits the Earth, it impacts with a velocity v naught. V naught is given as root 2gh, is the velocity with which it's going to hit the Earth. So now this is a head-on collision of two entities, Earth, mass. So this is very heavy, it's not going to nudge. So then this fellow will rebound. This particle will rebound with a velocity ev naught, right? And it will rise to a height, say h prime. Rise to a height h prime, where its velocity will become 0, right? So then 0 squared minus Vr squared divided by minus 2g h prime, right? So we have h prime is ev naught squared divided by 2g. Yes or no? If you launch it with a velocity u, then the maximum height reached would be u squared by 2g. U squared by 2g is the maximum height reached. So then this is e squared, and v naught squared by 2g. See, v naught squared by 2g is h. So h. So it rises to a height which is e squared times h. It rises to a height which is e squared times h. So it rises to a height which is e squared h. Yes or no? So now, once it reaches this point, it will fall back again, starting from rest. Now it falls from a height e squared h. If it falls from a height e squared h, it will rise to a height which would be e squared times this. It will rise to a height which is e squared times this, right? So that means it will next rise to a height which is e power 4h, right? No? No. If it has fallen from a height h, it has risen to a height e squared h. So that's the rule of the game. If it falls from a certain height, it will rise to a height which is e squared times the height from which it falls. So now, see, it has risen to this height, e squared h. That you understood? Right? That means now it falls from this height. So it will rise to a height which would be e squared times the height from which it falls. E squared times this height is going to be e to power 4h, isn't it? Now it falls from this height. It will rise to a height which is e squared times this height. So e to power 6h, and so on and so forth. Where e is a number that lies between 0 and 1.
Most of the time it has to be less than 1, or else it will bounce to the same height. If e is equal to 1, it
Yeah.
bounce to the height.
Yeah, but when did I say e is 1? Yeah. right? So eventually after a while it will rise to a height e to power nh, right? E is a number lying between 0 and 1. E is a number that lies between 0 and 1. Now, so eventually it has to settle on the ground after a while. That means this e power nh, suppose then e power nh has to become 0 if it has to finally settle on the ground. After a certain number of times, if it has to settle on the ground, then the height to which it rises after that time must be 0. Now this can be 0 only if n is very large. N is infinity. Because see, e is a number that lies between 0 and 1. H is not 0. For e to power n to be 0, you must raise it to a very large power, isn't it? E squared would be smaller than e. E to power 4 will be smaller than e squared. E to power 6 will be smaller than e to power 4. As you keep raising the power n, if you keep raising the power n, e power n keeps decreasing. Eventually when n tends to infinity, e power n will tend to 0. That means the number of times it rebounces, the number of times theoretically it rebounces is infinity. It rebounds infinite number of times, right? Now, the total distance it travels before it finally settles to dust is the following. It first falls from a height h, it travels a distance h. Then it rises to e squared h and falls back from e squared h. That means twice e squared h. Next, it rises to this height, falls back. So twice e power 4h, e power 6h, and infinite terms before it eventually settles on the ground. I'll repeat. I'm saying it falls from a height h, this. Then it rises to a height e squared h and falls back. So twice e squared h. Then it rises to this height and falls back from this height. So twice e power 4h. And it keeps doing this till the terms become 0. When would the term become 0? After infinite number of terms. So the number of terms in the sequence is infinite. Yes or no? And this will give me the total distance traveled. Do you realize that this is a GP series with common ratio e square less than 1? And sum of infinite number of terms of a GP series would be? Right, that's what we'll do. So this would be h plus twice e squared h divided by 1 minus e squared. 1 plus r squared up to infinity would be 1 by 1 minus r. I took e squared h common from this. So 1 plus e squared plus e to power 4 etc. is going to be 1 by 1 minus e squared. Right? This then is h into 1 plus e squared by 1 minus e squared. Right?